Now, good morning, everyone. Thank you very much to the team for inviting me, and it's well, a great idea to broaden your conference towards quantum gravity, and that's what I'm an exponent of, and it's my task to entertain you for the first and wake you up. Well, you couldn't have enjoyed reading my abstract because I never sent one in. So thanks for being here anyway, and listening to what I have to say about my life near the Planck scale. Maybe you're a little further away from it, but I want to tell you what it entails and what the joys and dangers are of this one. So let me jump straight in and talk about and kind of define my perspective. So what I want to do is to construct a fundamental theory of quantum gravity as a non-perturbative, diffeomorphic, invariant quantum field theory of dynamical geometry and study its properties in a Planckian regime. So every word here is important. Yes, so fundamental theory, so valid on all scales, that is non-perturbative, goes beyond perturbation theory. Well, obviously it's diffeomorphic, invariant, and one takes seriously the idea of dynamical geometry. Now, as everyone also knows, that is not an easy thing. So it presents us with major technical, physical, and also conceptual challenges. So one has to deal with, of course, the theoretical affinities, the absence of a fixed background, a space-time that prevents many kind of standard ways of quantizing the theory, and one has to understand what the theory is. One has to find ways and means to extract as information. And well, we will not. We have to do this because we lack the analytical skills. Tools. We have to do this numerically. Of course, we have to renormalize the theory, and obviously we want to connect, so that we connect in the proper way to the classical theory. And eventually, we want to derive new physical predictions. Now, this is a steep program, and let me tell you today where we are on the way to addressing and actually solving these problems. So, my methodology is, of course, of CBT, so-called causal dynamical triangulations. So I call this a minimal non-perturbative quantum extension of general relativity. So it uses very kind of few ingredients, and there's certainly no exotic extra ingredients. And among other things, what it does, it provides a blueprint that indeed, from such a framework, you can derive a quantum space-time. So in the best sense of the word, in the most direct sense of the word, emergence, without having put it in initially. So if you like, from some Planckian soup of quantum geometry, big quantum fluctuations at Planck scale, and we obtain some results, and it will give you a flavor of what you can expect to get out from such a formulation. It is fully non-perturbative, but again, that of course comes with certain features and you could say limitations. And of course, it gives us a certain idea of kind of what the theory is, quantum gravity. Now, for this workshop audience, I will highlight a few things. So I will tell you where, as I said, where non-perturbative quantum gravity is going, or at least ought to be going, and what it is like to live near the Planck scale. That means we design experiments, numerical experiments, we execute those experiments, we interpret them, and then we feed them back into theory construction. So it's a kind of computer-aided theory construction, because of course it's not there is a well-defined theory, like GR, and we just throw numerics at it because we can't do the computation because the equations are not linear. No, it's really trying to understand what the theory is. So it's something very fundamental. Okay, now what divides quantum gravity from quantum field theory of curved spaces? Well, at the risk of sounding negative, but it's almost everything. Well, the mathematical language is very different. For the Planck scale, it's very different. I'll be operating, I can tell you explicitly, in a range of kind of up to between 2 and 20 Planck lengths. That's where I can find results. Silent quantum fluctuation in this set of huge. Now, the type of computation that can be done, I have already highlighted, but what we can do in the non-perturbative regime, of course, perturbative things will be very, very different. You know, I have everything. I have tensor calculus, I have the power of analytics. Observables are also different. I'll comment on this later. During the course of the talk also, well, the status of diffeomorphism invariance, of course, it should be present, but it looks, again, very different, perturbatively and non-perturbatively. Background, independence, certainly the role of intuition. You know, I always get slightly aggravated when people talk about their intuition of what happens at the Planck scale. And also the type of kind of quantum effects that we expect. So we will be able to go beyond, let's say, H-bar effects, which of course is a natural realm of the perturbative theory, also it's an effective quantum gravity formulation of quantum gravity. Okay, now zooming in on the positives, and that will be also addressed during the conference, also by other speakers. You know, is there some common meeting ground? So what will emerge from my talk is, well, we are finding something like a space, a quantum space that emerges that has some disorder. Now, can that be used to link to kind of the early universe, where of course also the disorder space play a prominent role. And maybe some of the observables might actually be addressable in those frameworks. Okay, now, so here is kind of the fresh outlook from my perspective of what quantum gravity is these days. So we have a non-perturbative framework. It doesn't rely on any exotic ingredients and really on very standard also quantum theory. Now, so there are no revolutions in terms of technology. What it does is to take dynamical geometry spheres. We have a functioning computational network, which I call our lab, and when I talk about experiments, well, that's important feature, and it enables us to make quantitative statements, okay, with error bars about the properties of certain, well, the eigenvalues of certain quantum observables. And you also the methodology, this CPT I mentioned, you really should think of it as a tool. It's really like, you know, this is to gravity what lattice QCD is to a non-linear gauge theory, a tool that's non-perturbative and that enables you to extract information you cannot currently to extract with other means. Now, what's the demystification about? Well, it's just this standard phrase that everyone has of the fundamental incompatibility of quantum theory on the one hand and general relativity on the other. Of course, that's exactly what we are addressing in quantum gravity, showing that these things indeed are perfectly compatible in the right framework. What is a new feature I would draw your attention to, a way of looking at it? That's to say, okay, now, what's the mathematical foundation of GR? Well, obviously, it's, you know, Riemannian, pseudo-Riemannian geometry, which is extremely powerful, has been with us since the mid-19th century. But I would claim it's now inadequate to really describe quantum gravity, what happens to space-time at a very, very short scale. So we really have to think beyond Riemannian geometry. So what here I call, you know, beyond classical, and what is goes under the label of random geometry. And I'll tell you about this in a second. Now, what I like to quote, and what I find is fascinating, if you go to Riemann's habilitation thesis, which he had in 1854, he writes down for the first time the line element, ds squared, it was written down there, equal to g mu dx mu dx mu. But he also said in the text, you can just go and read online, he said, well, you know, for the time being, I think this is it. But there may come times where we will find from a physical point of view that this is inadequate as a description of geometry. And my claim would be, well, we have arrived at that moment now. Now, from the point of view, you know, of connecting to field theory, cosmology, so I think that's the most likely setting scenario that we may be able to relate to coming from quantum gravity. Now, there, of course, people think about a lot of applications, even desktop experiments, or solving the black hole paradox. These are very weak energy settings, semi-classical settings. But here we're diving into the non-perturbative theory, and the question is, what can we best relate to? What do we expect to be able to relate to? And I would say it's early universe quantum physics. Here we derive it from the full theory, which is of course qualitatively different from what you do, say, in quantum cosmology, where you rely on, before you quantize, on a very severe restriction symmetry reduction of the degrees of freedom. So here we are keeping all these degrees of freedom and then see how far we get with it. Okay, so what's the problem with quantum gravity? I should also say, now, where did all the trouble start? I would say the trouble really started in the mid-1980s, when it was finally confirmed that the perturbative quantum field theoretic formulation would not be good enough to arrive at a fundamental description of quantum gravity. So I'm quoting here these famous papers from this two-loop calculation by Borov and Zanotti, but of course people had already been suspecting for the better part of 10 years that probably this would be the case. So this is of course a formulation that relies here on this perturbative split of the Lorentzian form metric G mu nu into typically flat Minkowski space, eta mu plus some small perturbation, and the theory is then further treat kind of linearly in these H mu. Now, what's the trouble there? Well, the trouble then is, once you go beyond the standard quantum field theoretic quantization procedure, you can say, well, there is no canonical way of proceeding. And that's, of course, exactly what happened. People branched out in all kinds of directions to say, well, what does it mean to quantize gravity non-perturbative? Yeah, and you have, of course, the major program. So I'll be extremely brief about that, and refer you to my recent article, Quantum Gravity in 30 Questions, where I also kind of try from today's 2023 point of view to look in this broad brush at what has happened before in non-perturbative quantum gravity. So very roughly speaking, I would say until about the year 2000, well, there were big approaches that had originated in the 80s around, thinking lucid strings, and also in non-perturbative quantum gravity, people were arguing a lot about what is the best approach and whose approach has the most beautiful formal properties. But of course, no one could compute anything. A rather formal, a rather abstract discussion. So we didn't know what observables to look at. Now, in the last 20 years or so, this has changed. So we have indeed some new computational methods to allow us to compute things, as I'll also illustrate further on in the talk. Generally speaking, there has been also a reversion, away when I talk to strings. These, of course, take us beyond standard quantum field theory. But if you now look at the archives of what people have been publishing in recent years about quantum gravity, it's all back to good old quantum field theory, or almost all of it. And that's where I will stay. And specifically, the path integral has been having somewhat of a renaissance. Well, some of us have always worked with the path integral. So here it is already. So what is this dynamical triangulations approach in a nutshell? So as I already said, from a conceptual, from the point of view of policy, this is very conventional. We just rely on the good old quantum superposition principle as expressed in Feynman's path integral applied to gravity. So for simplicity, I'll stick to pure gravity. So where the path integral formally is this sum over geometries. So Lorentzian matrix modulo for dimensional diffeomorphisms, and so with respect to some a priori unknown measure of the space of geometries, this is the functional integral. Of course, you superpose all of these weights these complex weights that depend on your favorite gravitation. Okay, so that's a particle. So this is what I call a statement of intent, because you have to say, of course, what all the ingredients are in order to make, in the sense of this, and transform it into something you are actually able to compute. Now, so here, as I said, the underlying manifold M, and we want to, of course, compute this beyond perturbation theory, because this is not, this leads to, a perturbatively non-renormalizable quantum field theory. So we need to go beyond that. So what is DT, dynamic triangulations, or well, it's really a concrete realization to convert this very formal path integral into something specific one can compute it. So this was first done in the Euclidean domain. So I'm here just noting that the Euclidean kind of analog of this formal object, where well, the main thing that has happened, of course, it's a real thing with e to the minus s weights, where s is not the action of kind of some Euclidean space rather than Lorentzian space times. So what this uses is random geometry. So here I promised you to explain what this is, but random geometry is really the study not of individual spaces but of ensembles of curved spaces, which we approximate in a certain way. So we can compute with them. We approximate them in this Euclidean domain by looking at building blocks that, well, are typically chosen to be triangular for convenience. They could have another shape, and they're very simple. So they're equilateral. Yeah? So small elementary building blocks. And in order to get an ensemble of random geometries, we take these building blocks, n of them, where n will be a large number, and we compute always, bring them together to obtain, in some approximate way, in a piecewise flat way, curved spaces. It's fine. So that's the idea. So, and each of them, each of these fluids, you could say, of these building blocks, we weigh, of course, with something that is on these flat spaces, the analog of the gravitational action. So that's the story of random geometry. Now, this was born, this approach, it was invented by physicists in the mid-1980s who were interested, amongst other things, in describing non-trivial dynamics of two-dimensional worldsheets in what was then still bosonic string theory. So we was looking at, well, we want to make this non-perturbative, that will be recurring field in quantum gravity. How can we describe, how can we get a handle on these curved spaces? And people started kind of triangulating. But in that, it didn't really lead anywhere within string theory because it wasn't soon discovered. Also looking actually at these random geometric versions, it was soon discovered that the theories doesn't make sense. It's not, it contains tachyons. So that's of course when then where the story of superstring theory originates. But nevertheless, this methodology has then had its own life, as on the one hand was called non-critical string theory, but on the in another way as a two-dimensional toy model of quantum gravity, right? Because you can forget any embedding of where these two-dimensional surfaces may lie in, and then you have a toy model of intrinsic geometry in two dimensions. So that's what people started studying then, and what has in the meantime become an extremely hot topic within pure mathematics. So if you're interested in this, so what one studies there is one, what has this ensemble of random geometry, but one takes a continuum. So one takes a limit, where all the building blocks shrink to zero, and the number of them goes to infinity, and it's only interested in the behavior in the continuum limit of this ensemble. And very interestingly, well, one can say very much in an exact mathematical way about this continuum limit. It's a metric space. Of course, it's very curious, non-classical different properties. So look at this paper by Scott Sheffield for a beautiful introduction into, from today's community, two-dimensional, what we call the two-dimensional Euclidean path into the. Now, and here you see a typical member of such an ensemble, which gives you a flavor of how non-classical kind of these individual members are that contribute to this path into the. So what I want to highlight is that one shouldn't be surprised that they look, whatever they look like, because well, they're very quantum, if you like, and you should think of them as in two dimensions. Random surfaces are really the analogs of one-dimensional random paths. Yeah? And if you think, where do we meet random paths? Well, we meet them, for example, in the quantum mechanical path interval of a non-relativistic particle. When you construct, there is a way, of course, of constructing that in an exact way mathematically that goes via the sort of Wiener measure. And what you're looking at is the continuum limit of an ensemble of one-dimensional paths, which has interpretation in you go from point X to point Y. You superpose these paths and you take a continuum limit and you find what the measure is. It's something rather curious. From a kind of classical viewpoint, you find that the typical member of this ensemble is a nowhere differentiable path. Yeah. But there's of course no conflict with classical, this Ehrenfest theorem or extracting the classical limit from this theory. It's not an element of quantum theory. So something similar happens in higher dimensions also. Now, obviously, as so often happens, as I said, we have a beautiful piece of exact mathematics, and many people, working on this from statistical, combinatorial, analytical point of view. But what we need in physics is, unfortunately, a couple of steps further. Number one, you need to be Lorentzian from the Euclidean. Number two, of course, you need to be in four dimensions. And what does it imply for this scenario? So this is kind of the birth of CDT, yeah, which I, the birth help was by myself and Jan Ambio quite some time ago. So here we ask ourselves, especially the question about the transition from Euclidean to Lorentzian. So how do you do this? Well, number one, you need different building blocks. The building blocks are no longer that Euclidean, but they have to be flat Minkowskian. So that's the simple part of the procedure. But then you have also to invent kind of gluing rules for those, and we made a certain suggestion of how to do that, namely how to do it in a way that kind of maintains a notion of overall causal structure, and then you have to generalize this to four dimensions, and you have to show that it gives everything interesting. Okay, it's a long story which I will cut very short for you. There's another perspective from which one could look at this whole story, which is what physicists do when they're confronted with the quantum field series. They cannot analytically solve all this, solve with the methodology of standard perturbation theory. They put it on the lattice. So this is kind of reality check. You disregard everything you have, and then you just see, okay, what's the result, or where does that lead me? There's of course a time-honored way, for instance, to study QCD. There's a non-perturbable spectrum of QCD, but it's of course also a kind of standard way, talking about non-relativistic systems that people apply in statistical field theory. And only a couple of systems where there are no direct analytical methods available. So the lattice there, so what's the general philosophy? The lattice acts as a regulator, the space of the space-time. Typically, one chooses it to be a cubic lattice. The edge length of the lattice has the role of a UV cutoff. So I'm only allowing myself to look at the resolution of what I call little a, and in the end, of course, I want to send little a to 0. Then one searches for a continuum limit of the ensemble of whatever one has put on the lattice, and near a second or higher order phase transition as if A goes to 0. So what one also will have to do in general is to rescale or renormalize the bare coupling points. So that's part of this process. And if all goes well, one finds such a continuum limit, then it tends to be almost unique. I mean, we will still have some parameters floating around in the system, but the beauty of this way of setting it up is kind of the philosophy of critical systems is that in this limit where typically you have that's characterized by a divergent correlation length, the dependence on the arbitrary regularization details you put in when you set up these lattices, who told you what lattice to use, say, they drop out. And what remains is a continuous here, which is characterized by certain reversal properties. That forget about those details. So that's another beautiful thing. So so that's also the logic we apply to gravity, and it's distinct from what one might call discrete approaches to quantum gravity, where such a regularization or discretization is often thought that it's fundamental, an assumption about, let's say, space and at the Planck scale being discrete. So it's of course an assumption. It's many people intuitive that it should be like this. But this here takes a different stance, what I do. So, and the beauty is, and when I said a couple of times, this methodology, if you implement it correctly, it takes you, of course, into a realm where other methods don't really are not effective. Of course, it's subject to numerical limitations of all kinds, but we are familiar with dealing with them. That's again what people working in statistical mechanics or let's say lattice QCD do every day. So if it works, continuous theory is essentially, we may have a few parameters, but that's something we can live with compared with the embarrassment of riches that we have met in other approaches to quantum gravity. Now, this what is called what I hear called lattice gravity also has a history. So people really were very much motivated at the end of the 1970s. So that's in the distant days of the last century. They were motivated by the successful theory of lattice QCD. And if you now look, 40, almost 50 years later, of course, what people can do in lattice QCD is just amazing. They can just compute particle spectra, right? From very limited, stupid little lattice computation. So it's very powerful too. If in quantum gravity we were kind of morally speaking and technically speaking where lattice QCD is today, I think we could be very, very happy. We're not quite there yet, but we'll get there. So these early attempts of trying to put gravity on the lattice tried to very much emulate also the formulation of Young-Mills theory, gauge theory, namely putting where it was natural to put connection variable, an integrated potential on the edges of a lattice. And that we can to some extent take over when you start in the first order formulation. So that uses pure binds and spin connection instead of matches. But it's otherwise, of course, classically equivalent. So this type of first order formulation is what people put on the lattice. Well, to cut a long story short, many versions were around. People did put them on the lattice. They tried to do computation with them, but they never found anything interesting at all. Any hint of that there might be a continuity. And with hindsight, I would say then really can attribute it to the fact that just by putting, these classical fields on a lattice, one thing one does is, of course, when totally breaks the moment, it's so broken that you cannot even point to where it has gone. Of course, on fields on a lattice, this symmetry simply doesn't act anymore. Now, then parallel to that, what I would call a not so naive approach to putting gravity on the lattice emerge, and it's based on, it's much more geometric, and what DT and CET are basically kind of the modern implementation of that idea, and it goes back in the physics context to Redshift, who in 1961 wrote a beautiful paper about general relativity without coordinates. So what was his intention? What was his aim? He wanted to solve the Einstein equations away from situations of high symmetry. That's of course where our textbook of GR present solutions, therefore cases of high symmetry, spherical symmetry, cosmological symmetry. But if you're not near any such highly symmetric situation, how do you solve Einstein's equation? Well, of course, nowadays we say, well, you just solve them numerically in some scheme. But his idea, in addition, was how do we attack this problem without running into this annoying problem of having to deal with gauge covariance and extracting the physical, just working with the physical content of the degrees of freedom, which is don't sit in the metric, but sit in the metric up to a coordinate. So, and the beautiful idea is if you discretize your continuous, your smooth metric spacetimes M with some GMU assignment into a lattice. So what is a lattice? Well, the lattice is just an equation, you know, of triangle of such. And again, he was working with triangular building blocks. Where is the geometry? The geometry sits in the edge length assignment of these building blocks. The building blocks are flat in the interior. If I give you all the edge lengths, the interior geometry is totally defined. So you glue these things together and you obtain, you know, objects with curvature. That's the idea. And that's what he did. And he wrote down an equation in this framework. So as functions, also these dynamical variables, these variable lengths of some given triangulation. Now, this had, I would say, moderate success from the point of view of numerical relativity. People have occasionally looked at this, but the full power of this idea really emerges in the non-perturbative quantum theory, in the non-perturbative part. So that's what I will contain. So what is the CBT implementation of this? Well, it's really slightly different from what he had in mind. It's not fixing a lattice structure and then letting the edge lengths vary, but taking all the edge length equal and let the gluing vary. Yeah? In this way, kind of you get to these ensembles I talked about earlier. And well, the beauty of this is it's kind of number one, manifestly background independent, because you're not distinguishing any given spacetime. You're just doing kind of democratic sum over all of them. Yeah, and then see what happens. And what is diffeomorphism? It's manifestly diffeomorphism invariant. Well, there are no coordinates that's already registered inside. But of course, when you work with these triangulations, we have to label the individual elements because we have to tell who is whose neighbor, for example. And but this labeling is very easily kind of put out already in the process of how we set up these. So that's it. You're working with pure geometry. And I would say it has beauty. It has the beauty of the spirit of Einstein's theory. It's what and cloth. Yeah, so not metric. So here is the path integral as it's being made into a complete computable expression in the framework of now CDT quasi-dynamics. So here on the left-hand side, again, you have the same form of path integral I wrote earlier. G of M is just this quotient I have, and S here for definiteness I take as the Einstein-Hilbert action with a 4-dimensional Ritchie scalar and cosmological constant term. So now we are translating this into this random geometric framework where my the space times are represented by triangulations, so Lorentzian from Lorentzian building blocks according to some new rules. Here there's a simple matter factor, which is where T is the number of discrete symmetries given triangulation T made F, so the number of non-trivial ways it can be mapped onto itself. So if it has such symmetries, then it has a lesser weight in the sum, but otherwise it's the same story as here. You have simply now a sum over all objects of the type we are considering, where each of them is weighed with a kind of simplicial analogs, the Reggie action, we say, of this continuum action. Again, we're not interested in finite triangulations. That's why there's this limit here. So we're interested in a continuum limit of this, a scaling limit, more precisely speaking, where the number of building blocks goes to infinity, and where you're imagining that you're holding a finite volume constant. Yeah. So A is kind of the lattice scale, so that sets the length, your edges, and your simplicial building blocks. This is a 4-dimensional continuum volume, which is dimension 4. So A is dimension 4 of the dimension of length, and is just a number. So that's the idea. Now, I haven't said anything about the Boole rules that we adopted in the CBT framework, where it's an analog of what is a very strict properties that's imposed often in asymmetry are, which is global hypermobility. So where you really can think of space-time as a sequence of light, which also for the purposes of topology is not allowed to change the topology, but where you have a very strict notion of also structure. So you wouldn't have to do this because in the path integral, no one tells you a priori, and there are no strict arguments that tell you a priori what kind of spaces you should be summing over. So what we did is we pull up with a specific system, and then we could show that gives you totally different and much more interesting result than the previous story. Now, because anticipating that we have these interesting results, so with hindsight, we interpret it in the following way. So you could say, okay, you're putting in a causal structure by hand, but shouldn't that kind of emerge? It shouldn't kind of time emerge. I would say that was part of the philosophy of the Euclidean path into retrieving quantum gravity. Yeah, that was promoted by Hawking and this was very much starting from the 70s. Well, also quantum cosmology, but also beyond, and which was of course never found to work. So, but there the idea was, let's close our eyes, let's start with Euclidean path integral. We have no idea how it relates to the Lorentz path integral. Let's solve this, and then some beautiful thing will come out, and then we will kind of rotate it back and interpret it in physical terms. Unfortunately, step one of this program never worked. There was never anything interesting coming out that I could have rotated back. So what we're doing is different. We're starting here. We do have in this formalism, the CB2 program, we do have a well-defined rotation. So this something that of which there is no continuum analog, but we need it in order that we can compute them beyond 2 dimensions what the possible. But again, it turns, so we're putting in really that there is a kind of flow of time. We're putting this into every single contributing history of the past. And then it gets very interesting. Okay, again, so this is the building block, an elementary constant building block, just to have shown it to you once. So it has time-like edges and space-like edges. And in the middle is, of course, just a piece of completely regular flat in constant space. And then, of course, we start doing these together. Okay, so we have this framework. So what can we do with it? What are results? Well, we in this game, as generally in non-determinate quantum are observable. So, someone comes to their theory of quantum and you ask, what are your observables and what are the results of these observables? So here, when you work with a path integral, an observable, has to have, of course, to be differomorphic invariant. And you're interested in the expectation value of that in the ensemble you're looking at. So here I'm writing down already kind of the rotated version, if you like, of the setup, that you have a normalization factor, 1 over the sum of the geometries, and then you insert your favorite quantum observable here into this integral. And that this then has the interpretation in the suitable setting of the vacuum expectation variance. Now we come to the tricky part, which is kind of what are these observables in the context of a non-determinative theory? Well, the fact that they have to be differomorphic invariant more or less implies, well, there's certainly, but it cannot be just local quantities, like the Ricci scalar at a point x, but they have to be, for instance, non-local integrals of such scalars. And why is that? Well, in pure gravity, the thing is, if I would just stick with an R of x and was given the task of evaluating its ensemble average, if you like, it would be impossible for me to understand what I mean by the point x in the ensemble, because I go through the ensemble and the task is then to find the point x, but x is later. So the whole point is, of course, in diffeomorphism, in this diffeomorphism invariant theory, unless you put in other stuff like matter or specific boundaries, there is no, you don't have any grid to refer to, no references. So therefore you have to integrate these things into non-local observables. Now, at this stage, there is some expectation management, what I would call. So your favorite semi-classical question will typically refer explicitly to some coordinate systems or to some stuff of knowing what the point is, and unless you give me an implementation which doesn't refer to such background structure, it will probably not be implementable as an observer in this setting. But this is not, well, this is a feature, yeah, and it's approach independent, but it makes, of course, the story interesting and quite different, again, from a setting where I work with a given background. So, is there anything we compute in such a setting? And there's already what I would call a quantum signature I can point to. So it's a true kind of non-perturbative observable, where in CDT we first found a true quantum behavior. So what is that observable? Very speaking, is what we call the spectral dimension. The spectral dimension of space-time is, or any other space, is a dimension expressed by studying the diffusion process. So, if you let a drop ring fall into a bucket of water, you can monitor the spread, into what volume the spread is a function of time, and from that you can reduce what the dimensions of space. And the same principle can be applied in very general contexts, among them these generic ensembles, and we found, to our great surprise, already some time ago when we studied these quantum gravity in 4 dimensions, non-perturbatively, that, well, on large scales, this dimension is 4, so that fits a classical expectation, but then when you approach the Planck scale, it kind of reduces to a number 2 or near 2. It's very interesting, number 1, it's a number we can compute, in which many other people have computed, and it gives you a tool already to compare different theories. And maybe surprisingly, people who did repeat in their favorite approach this kind of computation often ended up with a similar result. So to the extent that people have speculated, and Steve Carter is one of them, that this may be a universal feature of quantum gravity. So here we are talking, we're not talking about comparing whose formalism is the most beautiful, but we are comparing complete numbers. So I think that's part of the way to go. Now, to understand 4-dimensional quantum geometry will require more than just dimension. So here we need to really understand geometry. So, and what can we do? So the key early result that really makes the CD2 approach stand out is that we could show that for one property of geometry or magic, a very coarse one, where we monitor the 3-dimensional volume is a function of property. This we can map. If you look at the expectation value of this quantity, I call it the average shape. If you look at this really in the deep quantum regime, we find it has a specific shape, and the shape is shown here. These are measurements of V3 of T. Already, I mean, superposed. This is already the expectation value as here. So what they do is there are 2 curves underneath these red bars. One is the measured curve for this expectation, but the other one is the prediction for what it would be if you're looking at a classical Sitter space. So a classical, we can give the Sitter space because we are expectations to be able to do the computation, but it's the space we characterize in a proper time, line element in this way. And you can see here, the cosine square, it becomes a cosine cubed when you compute the 3-ball. So this is what we found derived from first principles. So that's very interesting. The red things are not error bars, they're the sizes of typical quantum fluctuations in our system, in the computer, the Planckian quantum space that generates these generated. Now, the thing is, I could say, we found the Sitter universe from first principle. That's not correct, because we've just identified one observable associated with the Sitter space, which you might characterize as a namely the global models, the conformal models, right? And you put mismatches, and you've also shown that actually the low line eigenvalue spectrum of the fluctuation runs also matches the semi-cluster expectation. But we haven't said anything about local geometry. So local geometry still looks like this, more speaking. Yeah? So averages, of course, if you're lucky, can look nice, but this is what the thing looks like locally. So can we say anything about our candidate? Of course, what we'd like to say is, what features in the cluster district is the highest symmetric space of the constant curvature. Can we say anything about curvature? Can we say anything about the curvature of an object like this? A lower differentiable object. We are clearly evaluating in any time we say a Riemann tensor on this will just lead you nowhere. It just gives you infinity. So, but to cut a long story short, because also I'm rapidly running out of time, there's new mathematics that gives you beyond Riemann notion of Ritchie curvature, which becomes a normalized modified notion in our quantum set. So what is this? In a nutshell, so you can go away with a flavor of how one might attribute curvature, more specifically Ritchie curvature, to an object that's totally non-smooth. So you don't have tensors, you don't have, you have only a notion of distance, so it's a matrix space, and a notion of volume. Now, it really is born from very interesting and exciting development in pure mathematics. And in particular, it's inspired by what is now called the Olivier-Ritchie curvature. So this is the French mathematician. So what one uses is the following setup. We are in D dimensions. We are considering, so we know what distances are. So we understand what, so in a positive signature setting, what spheres of a certain radius are. Geodesic radius epsilon. So we look at two spheres that are in each other's neighborhood, both of radius epsilon. Their centers will be, separated by some distance delta. And then what we have to do is in addition, we have to compute how far this sphere is away from that sphere in the center point sets. So we have to stick in a notion of distance for this object. So once we can do that, we then compute the distance of the sphere, which I call d bar, and we still have the distance of it. And then the beautiful key idea is on a metric space that has positive Ritchie curvature, this sphere distance is smaller than the distance of that. And conversely, for negative Ritchie curvature. So it's something one try to imagine it in 2 dimensions with a kind of saddle point geometry. So this is the geometric insight. You're converting this into a definition of Ritchie curvature in any that's beyond the smooth scale. So in the smooth scale, you can rewrite as the normal standard Ritchie curvature in this way, but with the beauty is that it generalizes to non-smooth spaces. And what we do actually in our homeography application, the set is the absolute delta, so we have on the signal scale, and we use kind of the point, the average of the distance of point pairs in this very simple manner to compute what d bar is. So what do we then do when we have computed these two quantities? We take their coefficient. So remember, d bar was larger or smaller than delta depending on the Ritchie curvature in the direction of the two spheres. So basically what we are getting is something, a constant term that's non-universal and a term that captures delta dependence. So when you change the size of the sphere, you will throw Ritchie curvature at that cos-grain scale. So when you change the scale, this will typically change. And that's not a flat state, then nothing will happen. You always look flat, and d bar will always be equal to delta. So this cannot be used to construct an observable. By doing these measurements of the sphere distance and averaging over our space-time, then we get something that's a kind of a quantum Ritchie scalar. And so then we measure it as a function of delta, but we need to compare it with something. It's not a quantity that's usually computed. When you do it's a kind of quasi-local object. So here we computed for very simple Riemannian model spaces. Flat space constantly curved negatively spaced hyperbolic space in the spherical constantly curved positive space. And we see characteristic behavior of this protein as a function of delta. And this is what is kind of a fingerprint of a geometry. And this is what we compare our quantum measurements to. Just to say that we can say that this has been done, this certain result. Let me just flag some pictures. So this is CDT in 2 dimensions, the toy model of quantum gravity, Lorentzian quantum gravity. We are measuring this expectation value. And here, that's what we find. You should look, so this is taken for various lattice sizes. What we're interested in is, of course, the infinite lattice size. So most representative of this yellow curve here of the dots. So these are up to systems of up to 600,000 building dots. We're measuring this Ritchie scalar, and what we find is this curve here. So if this was flat, in this quantum sense, well, it would be a straight line. This seems to be there seems to be some deviation from flatness, which is fine because it's just a quantum system. It doesn't even have a nice classical. So that's to say this is applicable. In the Euclidean case, I would say it's even more dramatic what we find. There, it's generally this is what the typical geometry looks like. Can we assign any? So it's a topological two-sphere. Can we assign any curvature to it? Well, we are evaluating our cartoon there, and we have mapped it in in a region where we can reliably extract canonic measurement data to the curvature profile of a sphere, a classical nice sphere, but there's an interesting twist. The best map is to a 5-dimensional continuous. So this is very non-classical, but it shows you that it works. We can apply it to 4 dimensions. This was what motivated us in the first place. We have a specific candidate out of there. Can we say anything about its curvature? Well, now we can say something about its average curvature. In its average curvature, again, we measure the size of up to 1.2 million building blocks with 4 dimensions now. This is where they is done with the former PhD student of mine in Australia. And again, when you find given the limited size of the passive organization, a decent match. So that's beautiful. So, like next to last transparency is this. So you strengthen for our 4-dimensional decision use, you strengthen the evidence that it does actually have something to do with the decision space. We have looked at the average curvature, but that is not fine-grained enough. We're still not saying anything about local. We have integrated over this. But so we are looking for fine-grained observations. And again, going back to the fact that, well, the classic superspace is maximally symmetric, the next idea was, can we show that in some maybe emergent, under force grain, our quantum is homogeneous and isotropic. And we can construct non-perturbative diffeomorphism in current homogeneity method, and that will be subject of the next talk after me of Stephen. We will be waiting for this slot. Now, another thing I want to briefly highlight is endpoint, because that's ubiquitous and it also appears when you do pure empirical space. So, what may not be known in general is that in non-perturbative quantum gravity, there are diffeomorphism invariant endpoint functions. So simply let's look at two-point function. So what are they? Well, here I wrote down an example of a 2-point function for some local scalar. Oh, it's an integral over all space-time, so we will continue the expression. We are in Euclidean settings, so here is a real weight. And then what you do is you insert this operator into x and y. That's standard. Now, you make sure, of course, the distance of these 2 points has to be measured with respect to geodesic distance. So it's a geometric object to satisfy the diffeomorphism design. So this is what this delta function achieves. Yeah? And then we have to integrate to make this again a diffeomorphism very close. You have to integrate over all insertions of x and y. So it's a double integral over x and y's where I make sure that the distance is perfect. Now, that gives you beautiful, and that's a 2-point function, depending on a geometric R, radius, distance, but it has, so this is completely sensible as a construction, right? And it's geometric. It has a little twist, because note, of course, we are not working with respect to background, but this to be an integral of all geometries. So not only is O of X and O and Y an operator level, there's also an operator dependent on the data function. So where do you then see on this, when you stumble on this, when you try to define what a connected two-point function is? You know, not only you would just subtract expectation value of O squared, but unfortunately, if you do that, well, that's not enough, because this little friend here, yeah. So you don't, naive subtraction doesn't produce anything that converges close to zero for large y. And then it dawns on you, oh no, well, this is a non-perturbative two-point function. So we have to do this. You started studying this, so I'm just showing you that in a two-dimensional example, we have already studied this on this type of Lorentz shooting quantum gravity. So this is a beautiful picture that one of the master students, Jesse van der Dam, has produced. So that brings me definitely running out of time in the last minute to summary and outlook. So I hope I've given you, a flavor of both. My approach of looking at non-perturbative quantum gravity is, so I call it computer-assisted quantum gravity theory construction. So we're having these, we can do these quantitative numerical experiments and look at what happens and also kind of things that back into theory. But of course, it looks, this is not solving an exact equation that describes Planckian quantum gravity. So it has a different flavor. And this is what this expectation management is about. Well, what can we do? We can compute and compare observables. I would say that's already a great thing, and something one can approach independently, compare with other approaches. We're looking for universal aspects of these observables, and looking for new observables, and we're looking for quantum signature, like set of spectral dimensions I've shown you. And the beauty is, well, so this has to be there somewhere. So there is the structure there. And as I said, from a mathematical point of view, well, we explore beyond Riemannian geometry, ensembles of such geometry. So it's random geometry, it's beyond Riemannian concepts like this quantum Ricci culture I agreed to introduce to you. So here again, we are, at a minimal quantum extension of GR, no pros, and nevertheless, despite these very sparse ingredients, we can show, in many aspects that a quantum space and with certain recognizable classical aspects re-emerge from first principles. And as a clear path to early universal phenomenology, I could have expanded more on, but I didn't have time. The stuff already led to the previous transparency. So we're looking at emergent symmetries, which are of course a fine grained concept like homogeneity and the emergence of structure we connect to. Now, more about this interesting use, and I've exhausted everyone's patience and attention span, and thank you very much for your policy.
All right. Thank you, Renate, for this very beautiful talk. We have time for 2 questions, 3. Okay.
Thanks for the talk. Thanks for the talk. It was very, very interesting and clear to see your methods in quantum gravity. It was really cool. Now, the question that I have is, when you compute the path integral and when you're computing the expected value of an observable, you must pick the observable, but also the state. So what is the state that you're, and this is associated with the boundary conditions of your path integral, right? So what's the state that you pick in order to compute these expected values?
So really, I'm projecting onto the vacuum state. What is the vacuum state? The vacuum state is the state that has in this formula has the lowest computing action, but the effective action at the Planck scale, we of course have the contribution of their action, but also has the contribution from entry to the level. So it's a very non-perturbative quantity that governs the level. So it's really the ground state. So when I say the zipper, so this is not just any of this is kind of the number of all vector, and you're also completely correct. Of course, that in principle, the only thing I can still change here are boundary conditions. So I'm of course confined because of computer to compact boundary conditions. So there's no asymptotic regime everywhere. So we are working, we are giving the spacetime typically start asleep, 40 slightly, and we have a cyclically identified time for convenience in the time direction. So that's what it is. Interestingly, so we could say, okay, yeah, but that will bias something. Well, again, it's not quite as simple. It's not very important. What theology from the black way, and what we are finding is we don't want to be a cylinder, and everything's something that it wants to be, it wants to be forced here. So I would say, so to some extent, the dynamical system overrides, part of what I put in as boundary. So that's also very interesting. But otherwise, it's exactly the expectation that I see.
Thank you.
Okay, we have another question over there.
I thank you a lot for the talk, Renate. Is any way in which one can connect CDT with perturbative quantum gravity, like the natural observables that you compute there, assuming asymptotic flatness are scattering amplitudes? Here, you're computing something rather different. So is there any connection?
So I would say, yeah, scattering amplitudes, I think totally out of the question. I mean, there's not even any asymptotics here. My quantum universe are, as I said, 20 Planck lengths across, roughly speaking. So, and they're so quantum-fluctuating. They are miles and miles and miles away from any, semi-classical regime. Nevertheless, as I showed, some observables, more like this cosmological observables, can we have expectation values that emerge on slightly lower scales that can be matched to the classical theory. But I would say, no, and graviton scattering here out of the question. And I would argue that graviton scattering is actually is a physical observation, so can be actually accepted out. So that's taken into different universal questions. So some observables, but this cosmological types, I think has the best chance of being matchable to a more standard situation, like our universe description, including QFT with a physical like vacuum state. Random fluctuations, having coupon functions, of course, that relates already morally speaking to what one finds in this kind of pre-inflationary.
Thank you a lot.
Okay, one last question over there.
You can mention about universality classes, what you're going to give them, what can you comment?
Yeah, well, of course, I would say number one, this type of lattice approach is in principle able, I would say, it only means to really verify that there are non-trivial substances that go beyond truncated frames, where of course one has collected very strong evidence in asymptotic state. It's a longer story. It's thinking very difficult in my instance. And but what has as you're probably aware, also that happened in the Radboud group, that because people have tried to reproduce or to find to compare results, say, before the profile, and they're definitely for some of the parameters of one can sure be but some matches can be established. So I think that's again the most fruitful way of proceeding via comparing observables. And I would say at this stage, I think they could, we could be seeing aspects of the same broad ID here from the right side. That's not at all excluded. So I think of them really as complementary functions.